Hello everyone, so in this particular video we'll be talking about BCE loss or binary cross entropy loss, and let's look at the documentation. So as it says torch.nn.BCELoss. So if you look at the theory, it says criterion creates a criterion that measures the binary cross entropy between the target and the input probabilities. So basically we'll be looking into this, okay, this formula over here, and we'll try to figure out how it works. So BCE loss is used for binary classification. So let's say you have a neural network over here, you have different neurons, there are many layers over here. Okay, so let's say there are 3 layers here, and at the last there has to be one neuron. Okay, so all of these are connected over here, all of these are connected, and all the neurons from this particular layer are connected over here. Okay, it's connected to this one. Here what you have is this particular neuron is going to output, let's say there is also a sigmoid function here, there's a sigmoid function here. It is going to output a number, let's say x, which is going to be from, so x ranges from 0 to 1. Okay, so it ranges from 0 to 1. It can range ideally from 0 to 1. Okay, it cannot range because sigmoid is applied, so it will be anything between 0 and 1, but never equal to 0 or 1. Okay, because sigmoid is applied. Sorry. Now the idea is we have to calculate BCE loss. Now the problem with this is that this is singular value, right? So x is singular. So what is x? How is x represented? Now I'm not going to get in detail in the theory because I already have a video in this channel with regard to that. However, I'm just going to give you a basic understanding. So it will be something of more of a revision. Okay, so this is probability of positive class, of positive positive class. Okay, what does it mean? So if you are, let's say, doing cat versus no cat, so this is probability of cat. So what is probability of not cat, or what is the probability of the negative class? So 1 minus x is going to be the probability of, it is going to be the probability of negative class. It's going to be probability of negative class. Okay, so what is BCE loss? BCE loss, the formula says it is yi. So this is y is the real, what to say, your real label. Okay, into log of x. Okay, so plus 1 minus yi into log of 1 minus x. Okay, so this is your, this x is your probability and y is your real. So you take all of that here and then you have a minus sign in front. Now there is also a weight over here, but we'll just keep it for okay, let me just add it here itself. Okay, so there is also a weight which I will discuss in a couple of seconds, but this is the entire formula. Okay, this is the main part of the formula, right? So let's get back to the what to say, your documentation. Now whenever you talk about BCE loss, what you have to concentrate is the n, that is the batch size. So generally what happens is, let's say you have this neural network over here, you don't give one example. Okay, you don't give one example, you give n examples. So the input is going to be n cross, let's say there are 5 input neurons, so it's going to be n cross 5. So what is going to be the output? Since there is only one neuron at the end, so there will be one output for each example, so it's going to be n cross 1. So that is what it is saying. This n actually represents, it's also saying here, the batch size. So when you have so there are 3 you can see over here, 3 or 4 of them parameters. You have weight equal to none, which we'll be saying in a second, size average equal to none, reduce equal to none, and reduction equal to mean. Okay, now size average is equal to none is deprecated, and result equal to none is also deprecated, because both of the functionality of these 2 parameters is already inside the reduction equal to mean, and this is a new parameter which we'll discuss in a second. So we have to first discuss reduction, because this is something that we have already seen in other examples as well and other functions as well. Now we will be seeing reduction. After that I'll be seeing, or I'll be teaching you about weight. Okay, so we have understood this particular your function. Now n is the batch size. So what happens when reduction is not none? But he's saying when reduction is not none, we follow this, we take the mean, if reduction is equal to mean, and sum of L is basically the loss is summation of all of this, L1 L2 up to Ln, where Ln is what we have discussed already. So first let's take the condition where reduction is none. Okay, when reduction is none means not this case. So what happens there is you will have a vector, because reduction is not there, so you'll have a vector, because everything the whatever the output of this will be there, that is n cross 1, is going to be what, a vector only, n cross 1. So like this, or 1 cross n, whatever, but the idea remains the same. Okay, so what you'll have over here is some values, let's say n values. So we'll say o1 output 1, output 2, up to output n, or let's just call it x only. So remove this, because in the formula we have x, so you have x1, x2, dot 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 up to xn. Okay, so here also you will have x of i and x of I, right? So you have, this is your outputs. So you also have y values, so y1, y2, which is the yn, which is the real value. Okay, so for each xi and yi pair, we are going to use this particular formula, and this w of n will depend on I. Okay, it depends on I. Basically what I'm trying to say is, for, as I said, for every I from 1 to n, we will be applying this whole formula. Okay, so this should also be w of I, if I'm not wrong. Let's go back over here. Yes, so this is w of here they have used n, but n we have taken as all of the what to say, so 1 to n, let's capital N, all of n we have taken as examples, so you can say I for indexing. So basically for all the values over here, from 1 to capital N, we will have this particular formula applied on that. Okay, so we'll keep w of I separate for a second. So which means basically you will have for each and every xi yi pair, you will be finding this. So what you will have is, you will have a loss L1, L2, up to Ln, right? That is how, because L is what, L is your this loss, BCE loss, let's call it L of I. L of I is BCE loss of I, which is this formula. So since this is for all i's, so we'll have this many L1, L2 up to Ln. So when reduction equal to none, what we are going to do, we are going to give this vector itself. We are going to give the vector of L1, L2 up to Ln. Now I'm keep calling in vector because this is only for understanding. Okay, it's not a vector, it's n cross 1 instead of 1, n cross 1 instead of 1 cross n. Now when it comes to deep learning, generally we say this is the batch size. Okay, and for each batch you have one output. This is the interpretation. So when I say vector, don't get confused. This looks like a vector, that's why I'm saying like that. When reduction is not none, reduction is equals to sum. You do nothing, you add all of them, L1, L2, dot 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 up to Ln. So this is going to be your BCE loss, the entire loss. And when it's mean, you have already guessed it, L1 plus L2 plus dot 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 up to Ln divided by n, or let's have capital N, capital N, capital N. Okay, so here also capital N. So basically this is how it works. Okay, now so we are already done with this particular reduction, what it means. Okay, so whenever you have reduction equal to none, you have n cross 1 vector because of n examples and one output neuron over here. So n cross 1, you will just print it. You will not do any kind of a calculation. We will see the weight calculation, but ideally, since weight equal to none over here, as you can see, by default weight equal to none, which means no calculation will be done, this vector will be printed out. Okay, when you say reduction equal to sum, the summation will be printed out. When you say reduction equal to mean, the mean will be printed out. Now let's look at the second parameter, important parameter, which is the weight. Now one difference here with let's say cross entropy loss, because cross entropy loss also has the weight parameter. Okay, so cross entropy loss, which is used for multi-class classification, it also has the weight parameter, right? But here the weight is different. How the weight is different? So whenever you have this, you always have to think about reduction this is for understanding, reduction equal to none, which means your output is a vector of losses L1, L2 up to Ln for capital N. Okay, let me just go back here. Here we will have capital N. Okay, so when you think about weight, it is going to have, so weight is also going to be a vector. Okay, now it depends on the on the output, but weight is also going to be a vector or anything like that. So you will have w1, w2 up to wn. Okay, okay, so the vector of weight is also going to be, or to say, your w1, w2 up to wn. So what is going to be a final loss? The final loss will be this multiplied by this, plus this multiplied by this, plus this multiplied by this. So it will be w1 l1 plus w2 l2 up to wn ln. So let's say you want to zero the effect of this loss. You can say capital N over here. You can say w capital N equal to 0. If you want to zero the loss of L2, you can say L2 is equals to 0. Oh, sorry, not L2 equal to 0. You can say W2 equal to 0. Okay, so let's take an example. Let's take a simple example so that it is very, very clear. Let's say you have this simple neural network over here. Okay, and it outputs one value over here. You give it, let's say, 16 examples of 5 features. Okay, so what is going to be the output? It's going to be 16 cross 1. Okay, so let's remove 16 over here because it will become difficult. Let's say this is 5, let's say this is 6 itself. Okay, so let's say this is 6 into 1 instead of 16 into 1. So let's say we are taking the example. So our again, this is all there is after applying the sigmoid. So you will get x1, so this is x. Okay, this is x over here, whatever output you are getting after the sigmoid. x1, x2, x3, x4, x5 and x6. So this is your output. For this is the predicted. I am writing pred. Okay, now there has to be a real also, depending on whether the answer was 1 or 0. So let's just say it as y1, y2, y3, y4, y5 and y6. Okay, so there are 6 outputs as well. So 6 predicted and 6 real. So you take the loss function that I had said, loss function, and you will calculate L1, L2, L3, L4, L5 and L6, right? So you will calculate till L6. Now what will happen? If you don't have weight, then all of this will be, let's say, taken as a reduction equal to, if reduction is equals to none, if reduction, let's call this capital L, reduction equal to none, so you will have the same vector as capital L. If reduction equal to sum, then you will have summation of L of I, which is again going to be summation of this vector. Okay, and if you have mean, then you have same thing, summation of L of I divided by capital N. This is how it will happen. Now let's say let's assume values. Okay, let's assume values of this. So let's say this was 0.5, this was 1.5, this was 2.0. So L1 was 0.5, L2 was 2, L2 was 1.5, L3 was 2.0. Let's say L4 was 1.0, let's say L5 was 4.0, and let's say L6 was 3.0. Okay, so this is what we have assumed. Let's say our so this was L vector, right? This is L1 is this one over here, L1 is over here, L2 is over here, L3 is over here, L4 is over here, L5 is over here, and L6 is over here. Let's say our weight vector also, it need not be any kind of probability distribution or anything. It can be anything. Let's say this was 3, let's say this was 0, let's say this was 0, let's say this was 1, let's say this was 2, and let's say this was -1. Okay, or -2, whatever it can be. So what you have to do, you have to multiply this. So this is 1.5, this into this. As I said over here on the top, if you can go and see, you basically w1 l1, you see, multiplied the loss with the corresponding weight. Okay, so you multiply the loss here. What it is going to be, 1.5 into 0 is 0, 2.0 into 0 is 0, 1.1 into 1 is 1.0, and 4.0 into 2 is 8.0, and minus 3 into, what to say, 3 into minus 1 is minus 3.0. Okay, so this is your loss when reduction equal to none. Same thing if you have reduction equal to sum. So this was reduction equal to none. Okay, reduction equal to sum, you sum everything. So you sum all of this, you will have 1.5 plus 0 plus 0 plus 1.0 plus 8.0 plus minus 3.0. So this is 1.5, this is 2.5, this is 5. So 2.5, that's 7.5 is the loss total. Same thing for the mean. So mean is going to be, when reduction equal to mean, you have summation divided by the total number 6. So whatever this 1 point something something answer will be there. Okay, so I hope you understood the theory. Now let's go and see a practical. Before that, there is some more theory over here. So now you see this particular equation, right? In this equation there is a catch. What if x of I equal to 0? Now log of 0 is minus infinity. Now the problem with this is, so if x is 0, minus infinity. What if x of I equal to 1? X of I equal to 1, then this will become 0, because then this will become 1, this entire thing will become 0, again this will be log of 0. So now log of 0 is equals to minus infinity. This cannot work, because again nothing works with all this kind of infinity and stuff. Okay, and also if it is 1, if this is 1, then this will become 0, this will also become 0, right? So if y1 equal to 1 and x1 equal to 1, so if y equal to 1 and x is already equal to 1, so this will become 0, because the 1 minus 1 equal to 0, and this will also become 0. So this will become 0 into infinity, because log of 0 is infinity. So 0 again, all these things cannot be worked out, right? So what PyTorch has done is, they have mentioned it over here. The solution basically clamps its log function output to be greater than or equal to minus 100. So obviously whenever you have a situation where log of xi is getting lesser than minus 100, it just substitutes it to minus 100, which means if this is a function, so let's, f is the function, then f, the minimum value min of f is equals to minus 100, or let's say max of f is max of x comma minus 100. This is how it is going to work. Okay, so this is how it's going to work. That is the theory that I had to explain it over here. Okay, now let's go back to some code. So you this is the implementation of BCELoss. This is simple torch initialization of packages. Then you have two vectors basically over here, rand and basically the same thing, out and real. So you can see over here, this is the vector that we have. Okay, now first of all, obviously for the output, this is out is for the output of the neural network. After that you have applied the sigmoid. Okay, so you have applied the sigmoid, and then you have done reduction equal to none and passed simple loss. You have passed the activated output, which is sigmoid of the output, which is the final output of the neural network, and the real part, or the real values that had to be predicted, right? So you have done that already here. Sorry, you have found this particular vector after doing this BCE loss with reduction equal to none, and the reason you have got a vector, because you have said reduction equal to none. Now how to verify it? So you already have a vector, this act out and real is a vector. Can't we just apply the formula? I have applied the formula. It said, the formula said, if you go over here, it said y into log of x. Now what was y? Y was your output, real, right? Y was the real, so real into torch.log of act underscore out with activation output, plus, if you again look at the formula, 1 minus y into 1 minus y over here into log of 1 minus x. So you go over here, this is 1 minus y into log of 1 minus x. Okay, and then you add both of them and take the negative of the entire thing. So what you do is, you go over here and hit shift and enter. So you can see you have got the same values. This particular vector starting with 0.7 0.7451 is same as this particular vector. All the values match. Okay, again the first value is 0.7451, second value is 0.6897, here again 0.6897, and so on and so forth. Okay, again if you do instead of none, same thing. Okay, same, everything else is same. What I have done is I have just changed the none to sum. If you sum all of this, right, you will get this particular value itself. Okay, and you can see I have copied this entire thing I have just copy pasted over here, and at last I have written sum, that is summing it all. You can see both these values are same. You can see 8.5863 and here also 8.5863, which means these two things are same. Now again for the mean itself, so since we had 10 values, you just have to divide this by 10, and that is what you do. You divide it by 10 and you get this particular value over here. Same thing, I copied the entire thing, and instead of sum I have written mean, and it gives me that same value. Here also same value, here also same value. Okay, now let's say you are going to add the weight. Okay, so same, this one is the first line is the same. Here what I have done, I have taken torch of zeros. So this is basically torch of zeros of 10 means you have let me go over here, you have 10 values, all 0 0 1 1 2 3 4 5 6 7 8 9 10. So this is a vector of 10 zeros over here. Okay, so this is what it is, right? Now what you have said is at the 0th position and at the first position put 1. So at the 0th position, you have, this is the 0th position, you remove this and you put 1. And at the 5th position, so this is 0 1 2 3 4 and 5, at this position also you change this 0 to 1. So the final vector becomes 1, then followed by 1 2 3 4 zeros. So 1 2 3 4, then a 1, and then followed by 4 zeros, 1 2 3 and 4. Okay, so this is the vector that has that we have got after changing that, right? So this is what we did, and now pass it to the BCE loss. Now instead of just putting reduction equal to none, which has to be there in order to get a vector, I have also given the weights. So first I had all zeros, and then I changed two of the numbers over there. Okay, I have explained what that means, and then passed it as weight. So if you compare the vectors, you get all of the things 0 except the positions where you have not put 0, that is this position and this position. Now these are the same numbers that you had over here, that is 0.7451 and 0.6712. You can see they are same. Oh sorry, not the 67, 0.7967 if you remember over here. Here also you will have somewhere. Okay, wait, I have not run this, that's why it's different. Yes, so now you can see over here 0.6712, 0.6712, here also 0.6712, and here is 0.7451, here also you can see 0.7451, which basically means, now I have put a 1, if you put a 2 over here, this number might should double while the other number same. So this number has doubled, you can see, but this number has remained same, which means if I put a, let's say a -3 over here, or let's say -2, this number will double but become negative, and rest. So whatever number you kind of add it as a weight, it will reflect over here. Okay, so I hope you understood the logic and the video. If you like the video, please like and subscribe. Thank you very much, and bye.